Hello, this is MAT221. This is Mrs. Johnson. This is section 5.3 in Calculus 1. We were talking about this and we just did this problem on the calculator. Let's do another example, but this time I want to find what is the area between the x-axis and the curve y equals cosine of x from 0 to 3 pi on 2. Now, remember, if we use the fundamental theorem of calculus here, and we find the integral from 0 to 3 pi on 2, which we actually can do here, we should get a negative number, correct? Now let's just do the analysis here. Remember, if we find the definite integral from 0 to 3 pi on 2, that would be our values from 0 to pi on 2, which will be a positive number because the graph of this function lies above the x-axis. And then if we did the integral from pi on 2 to 3 pi on 2, we would get a negative number because this area of this curve lies below the x-axis. And we know that, again, if this is a derivative curve, this will be a critical point of the antiderivative. This point at pi on 2 would locate a local maximum because the derivative is positive, then 0, then negative. So we know that this would be its local maximum value. And then the curve would decrease, the antiderivative curve would decrease until 3 pi on 2. We do have another critical point. Looks to be, would be a minimum. Now, we could use the fundamental theorem of calculus here and we'd get a negative number, but that's not what this question is asking. This question is asking, what's this total area? It just wants to know what's this area here. So in order to find this area, what we're going to have to do is break up the pieces of the derivative function here into the positive part and the negative part. And then what we're going to do is either take the absolute value of the negative part, or in this case what I did was just take the negative of the negative part, so the negative would become a positive value. So let's use the fundamental theorem of calculus here to calculate this area. This will be positive, this would be negative, so we're going to take the negative of the negative. So let's first use the antiderivative here. The antiderivative of cosine is the sine of x, and I'm going to evaluate that from 0 to pi on 2. And then again, the antiderivative of cosine is sine of x, and we're going to evaluate that from pi on 2 to 3 pi on 2. So I'm doing a little bit of trigonometry here. We know that the sine of pi on 2 is equal to 1, and we know the sine of 0 is equal to 0. And again, look, I'm just using the fundamental theorem of calculus here, right? The antiderivative at the upper bound minus the antiderivative at the lower bound. So that is this piece there. So then I took the sine of 3 pi on 2, which is negative 1, and then subtracted the sine of pi on 2, which is positive 1. And then I just did arithmetic here. 1 minus 0 is 1 minus negative 2. 1 minus negative 2 is 3. Now, if you notice, if I took just the integral from 0 to pi on 2, which is this portion of the problem, this portion right here, this area right here is a positive 1. And if you think about it with symmetry, if I divide this bottom little bowl portion of the cosine curve in half, say I divided it by drawing a line right down here through the middle, notice this portion and this portion are going to cancel each other out. Now this was positive 1. This down here would be, if I go halfway across, would be negative 1. And then over here would be another negative 1 because of the symmetry of the cosine curve. So this would be 1, negative 1, negative 1, and you could see that that would give us 3 units. So this is like when they ask you to find, well, how far did a particle actually move, where we would take the absolute value or we would negate the negative portion of a curve. This does not give me displacement. This does not give me the actual definite integral from 0 to 3 pi on 2. the definite integral from 0 to 3 pi on 2 is going to be positive 1, plus a negative 1, which would be 0, plus another negative 1, which would be negative 1. So if we did this on the calculator, you could definitely see this. All right, so what I did was I turned on my calculator here and I put in cosine of x into my calculator. I set my window so that I'm going from 0 to 2 pi here. So, and I'm going to graph the curve. So here's the cosine of curve. It's a little bit longer than what we had before. Now, you can see if I just do my calculate menu and did the integral from a lower bound of 0 to an upper bound of pi divided by 2, notice it would just shade in that area right there, which we predicted before from our fundamental theorem. We said, well, that region was a region of 1, and it would be positive because it's above the x-axis. Now, if I had the calculator calculate the integral from 0, sorry, let's clear that, from 0 to 3 pi on 2, notice the calculator also shades in those regions for us, so that would be that. Notice I get an integral of negative 1. Now remember, that's what we predicted. We predicted that if this is a 1 unit, we noted that halfway across these two would look very similar, just in opposite sides. If we go halfway across, this would be negative 1 over here, and this would be negative 1 over here. So 1 minus 1 minus 1 would be a negative 1. So it makes sense to us what the calculator gave us. But what we wanted is we wanted the area. We just want to know the area. So anything that's negative, we don't actually want it to be negative. We want it to be positive. So on the calculator, or even by hand, an easy way sometimes to change the curve so that the curve will always be positive is actually to take the absolute value of the curve. So what I'm doing here is I'm going to hit the math button and go over to numeric, and then just use the absolute value function, which is number 1 there. And then in here, you could either type cosine of x. What I'm going to use is actually just say to the calculator, I'm going to hit the vars button, move over to y vars, and then put in y1. So it will take the absolute value of whatever's in y1. So if you notice when you look at the graph here, you can see both graphs. My calculator does it in color, so you can see the two different graphs. There's the absolute value curve. So if I do this here, and I wanted to now figure out what is the area underneath this curve, I could just use the second curve. So what I'm going to do is turn off the original curve by just going to the equal sign and hitting enter. It will notice that it's no longer highlighted. So the calculator will only graph the curve that's highlighted, which is the red curve. And then find the integral, which is number 7, from 0 to 3 pi on 2. Oh my, I got that one wrong. My cursor is very sensitive here. And notice it will shade in those regions and give us what we found before. Now notice, I want you to notice the calculator's a little bit off. We know it's exactly 3 because the calculator actually calculates the definite integral by using rams, believe it or not. And it usually draws in like 1,000 rectangles. So notice it's a little bit off, but we know the actual value, the exact value, is equal to 3 because this was 1, then this was 1, and then this was 1 to give us our units of 3. So it's good to note that the calculator is still not necessarily always exact as the fundamental theorem is when we do it by hand. All right, so let's go back to our PowerPoint. This we did by hand, and we found the exact value, which was equal to 3. So next what I'm going to do here, all right, so coming back to our PowerPoint, we figured out the area between the curves here, and we got the answer was 3. Let's try a couple more examples of the fundamental theorem of calculus. Now what I did here was I went to your worksheet folder and I found the first couple problems here on the worksheet to do. There are answers and other examples in the worksheet folder that you could definitely look at. So if f is a continuous function on the interval from closed interval from a to b, then we know that the fundamental theorem of calculus is the integral from a to b of little f of x dx is equal to the capital F of b minus capital F of a. In other words, remember, the accumulated amount of change is equal to the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. So we're asked to use the fundamental theorem of calculus here and trying not to use a calculator to evaluate these. So with the fundamental theorem, the first thing that we need to do is find the antiderivative. Now you guys should be pretty good at these from section 4.8, where we did a bunch of antiderivatives. So the antiderivative of x squared is equal to 1/3 x to the third. We don't need the plus c here because we're using the fundamental theorem, and when we subtract, the c's would simply subtract away, so we don't add that here. We evaluate the antiderivative at the upper bound and the lower bound. So evaluating at the upper bound, putting in 2 here, we get 8/3. Putting in -1, we get -1/3. And then subtracting them, we get 8/3 minus a -1/3, which is 9/3, or 3. So notice we found the accumulated amount of change of this antiderivative function over the interval from -1 to 2. All right, so let's try another one. Let's look at the definite integral from 1 to 2 of 3 over x to the 5th dx. Now remember, when we took antiderivatives with something in the denominator like this, if it wasn't x to the first power, what we did was rewrite the function so that we had a negative exponent, so we could easily do the antiderivative here. So first rewrite the function so that we bring up the x to the 5th to the numerator. And then we take the antiderivative, and the antiderivative here is going to be the 3 gets pulled out to the front. X to the -5 becomes 1 over -4 x to the -4. So here's our antiderivative. And then I just cleaned it up a little bit by bringing the negative out to the front and bringing the exponent back down to the denominator. Now we evaluate the antiderivative at the upper bound of 2. So putting in 2 into the antiderivative, we get -3 over 64. Then we evaluate the antiderivative at the lower bound, which is putting in 1 in for x, so we get -3 over 4, or -3/4. And the fundamental theorem of calculus simply says subtract those two values. So it would be -3 over 64 plus, in this case, minus a negative becomes plus 3/4, which is 45/64, which again is just dealing with fractions. This is the exact area underneath the curve, or it is the exact accumulated amount of change of this function, of this antiderivative function, over the interval from 1 to 2. Let's look at another example. This one says, let f of t represent the bacteria population, which is 5 million at time t equals 0. After t hours, the population is growing at an instantaneous rate of change of 2 to the t million bacteria per hour. Notice that's a rate of change. Look at the units. Estimate the total increase in the bacteria population during the first hour and the population at time equals 1. All right, so since the rate at which the population is growing is the derivative, right? It is the derivative of capital F, that we're given. The change in the population is going to be f at 1 minus f of 0, which, by using the fundamental theorem of calculus backwards, would be the integral from 0 to 1 of the derivative function. Remember, the antiderivative at 1 minus the antiderivative at 0 is simply the definite integral. Now, using the calculator to evaluate the integral, we could do this on the calculator. We could say, what is the integral from 0 to 1 of 2 to the t dt? And I got 1.44 million bacteria. So that would be this portion right here. we knew that f of 0 was equal to 5 because they said the population